Hello. In this video, we will study how to construct a confidence set, which is a generalization of confidence interval. Confidence set is for multiple coefficients, but confidence interval is for a single coefficient. So we will think about this general regression model with multiple regressors. So there are k regressors, but we are interested in only the first two variables, beta 1 and beta 2. The other regressors are just controls. And the beta 1 and beta 2 are important variables, and you would like to study their relationship, like which is larger or whether they are the same or not. So you want to analyze where the true values of beta 1, beta 2 are on a two-dimensional plane. Then you have to think about the two-dimensional confidence interval, which is a joint confidence set. But how to calculate the confidence set is a little bit different from the confidence interval. Confidence interval was kind of straightforward because there is only two directions, so it is just one-dimensional. So the error can happen either on the positive side or the negative side. And you just need to allow a certain margin of error on each side. However, in two-dimensional space, from the estimate, the error can be any direction. Error can happen any direction around like 360 degrees. So then how can we make the set that contains the true parameter with probability 95%. So the confidence level is 95%. That means if you use this confidence set, then the confidence set is going to be correct with 95%, but it has error about 5%. Equivalently, on equivalent approach, which I'm going to explain a little more later, is that you can understand the confidence interval as the flip side of hypothesis testing. So it is a collection of the confidence interval is a collection of parameter values, the coefficient values, which is not rejected by a hypothesis testing at the 5% significance level. Then, so 5% significance level implies 95% confidence level. So error probability is only 5%. So that is how we can understand the relationship between confidence interval and hypothesis testing. And we borrow the same idea to the multiple coefficients case, and we are going to construct a confidence set based on the hypothesis testing of a joint hypothesis, especially the F statistic. So we will consider the relationship between test and interval first. So in a single coefficient case, this is the starting point. Remember, you know that the confidence interval was calculated this way. So there is a point estimator, and you allow plus minus 1.96 times standard error. So 1.96 times standard error is the margin for error. So the error can happen this much. So you have to allow plus minus margin around the estimate. And we will study this in a different way. So suppose that there is a value b. B is in the interval. So b is a number in between beta 1 minus 1.96 and beta 1 plus 1.96. So b is inside the interval, right? So this inequality means b is on the interval. So, and then by simple rearrangement, like say subtract b on both sides and then divide by standard error, will give you this, right? So this means the difference between beta 1 hat and b must be in between plus minus 1.96 standard error. So if you divide that inequality by standard error, you get this inequality, which is equivalent, mathematically equivalent to the first inequality. And then this is a familiar formula because this is the t statistic. So in the middle, it is the t statistic for the hypothesis testing of this null hypothesis. So this null hypothesis, if you believe that the coefficient equals to b, then you would calculate the t statistic this way. And then if the t statistic is in between plus minus 1.96, you cannot reject the null hypothesis at the 5% level. So this shows the relationship between confidence interval and hypothesis testing. So any value in the confidence interval is not going to be rejected. It's not rejected. So, and 95% and 5%. Or vice versa. If a value is not rejected at the 5% level, then the value b should be included in the interval at the 95% level. So then now, if you use this idea, we know how to test multiple coefficients at the same time. That is the F statistic. And then using the hypothesis testing for joint hypothesis, we can construct a joint confidence set. So extend the idea. Suppose that you consider a null hypothesis such that beta 1 equals to b1, beta 2 equals to b2, and then you have to calculate the F statistic for this hypothesis test, for this null distribution, null hypothesis. If this hypothesis is not rejected at 95%, at 5% level, then those values, the values in the hypothesis b1, b2, must be included in the 95% confidence set. If not rejected, must be close enough to the true parameter, so should be included in the confidence set. So then what remains here is we need to think about what are not rejected. If you can calculate what's not rejected, then collection of those values makes the confidence set. So remember, the test was based on the F statistic. We know how to calculate the F statistic, and also the hypothesis was not rejected if the F statistic is small. How small the number threshold depends on the number of parameters included in the hypothesis. In this case, we have two parameters. So if F is smaller than 3, the hypothesis is not rejected. So we have to find B1 and B2 that implies F statistics smaller than 3. How can we do that? Let's have a look. So this is exactly what I explained earlier. And here you may use homoscedasticity only F statistic or heteroscedasticity only, heteroscedasticity robust F statistic. It doesn't matter. So choose whatever hypothesis testing you are going to use, and also this is consider the values that make small F statistic. So the collection of this is exactly the confidence set. And then automatically, if you choose 5% significance level, then automatically the resulting set will have a coverage of 95%. So it will be true. This confidence set will be true with 95%, as long as the test was 5%. Then it makes sense. This is a straightforward extension from one-dimensional case. And now it's mathematics. We learned F statistics formula is given by this, and we need to calculate when this becomes smaller than 3, which is not easy. It is not easy. So, but as a result, it is an ellipse. So it is not easy to calculate how we obtain the results, but the result is given by this. It is an ellipse around, so the middle point is a point estimator. This is the point estimator, and this circle is the ellipse is the confidence set, 95% confidence set of these two coefficients. So remember, beta 1 is the coefficient of student to teacher ratio, and the beta 2 is the coefficient of expenditure per student. And beta 1 estimate is minus 0.29, and beta 2 estimate is 3.87. But you have to consider all the possible values in this area, because this is where because of the errors, the truth can be somewhere here with 95%. What is interesting here is that so the origin is here. This is 0 point. 0 is here, 0 is here. So vertical axis is beta 2. Vertically, beta 2 is almost always positive. So 0 goes below the confidence set. So that means anywhere on the 95% confidence set, beta 2 is positive, right? However, what's surprising here is that beta 1, horizontally, the confidence set includes negative numbers, so it can go down to minus 1.5, and also it can go up to somewhere here like 0.8, maybe somewhere around 0.8. So beta 1 can be negative, or can be positive, or can be 0. So beta 1 is not statistically significant. This is surprising. So increasing the student to teacher ratio may not have any impact, or may have negative or positive impact. So from the data, from this analysis, we cannot say the student to teacher ratio has any reasonable significant impact on the test scores. So this is, however, we can also say that they are not both 0. At least one of them is non-zero, right? So because this null hypothesis, if you think about the null hypothesis, joint null hypothesis like this, then this must be rejected, because the null hypothesis implies this point, which is outside of the confidence set. So the distance is further than the threshold. So 5% hypothesis test will reject this. So that means at least one of them has some impact. Like here in this case, clearly beta 2 is positive. So because of beta 2 being positive, the rejection, so we need to reject H, because the second equality seems to be wrong. But the first equality is uncertain. We cannot say anything about the first equality. We cannot reject this one. So anyhow, because one of them is rejected, so we have to reject them jointly. Okay, this is how we set up the confidence set. And again, it is not easy to calculate this confidence set by hand, and there is no closed form solution. There is no clear formula how to solve out the area. But again, Stata can do it. But it is not commonly used. Just it is a good presentation if you want to make your report more look better. Then it is a good idea. But may not. I haven't seen it many times in many places. Okay, I'm going to like say in the next video, there are a few more minor issues, so I will discuss them in the next video. Okay, thank you for watching.